Okay, so we've talked a little bit about frequency, wavelength, amplitude, and the different types of waves, names that we've given them in the electromagnetic spectrum. And now we're going to move on to the speed of light, because every wave has a particular speed, and light waves have a characteristic constant speed. It's going to be page 2. So all light waves travel at the same constant speed. And you may have heard this talked about in physics before. It's called the speed of light, because it's a constant in the vacuum of space. So all light waves travel at the same constant speed. That constant speed is 2.998 times 10 to the 8th meters per second. And that's represented by the letter C. And the speed, which is a property of light, a property of waves, is related to two of the other properties, the frequency and the wavelength. Remember how we said they were inversely proportional? This formula indicates that. So the speed of light equals the wavelength times frequency. Let's label these. Speed of light, units, meters per second. Lambda represents the wavelength. Wavelength is measured in meters. And then nu is the frequency. And frequency is measured in things per second. So its official unit is 1/seconds. And there's another name for this unit. That unit 1/seconds is also called Hertz, abbreviated as Hz. So you might see that as well, especially when talking about radio or radio waves. We often use Hertz to describe those. So when we said that frequency and wavelength were inversely proportional, we meant just that. You can see that in the formula. If we increase the wavelength and this product needs to be equal to a constant, we need to decrease the frequency. And there's a different version of this formula. If you rearrange it to solve for frequency, it would be nu equals c over lambda. And this is a common joke that physicists say to each other. They say to each other, "What's new?" "Oh, c over lambda." It's an easy way to remember that formula, even though it's a really, really corny joke. All right, so we've got frequency, wavelength, amplitude, speed, and now we're going to have an example of speed to make sure we can use this formula. So let's look at the wavelength of GPS signals. So GPS signals operate at a frequency that is very low, 1.575 gigahertz. So hertz is a unit just like seconds or meters. You can add prefixes to it. So find the wavelength of this GPS wave in meters. Okay, no problem. We notice that if we have the frequency, we can convert really easily between frequency and wavelength using the formula for the speed of light. C equals lambda times nu. And we're looking to solve for wavelength. So we can just rearrange that to have wavelength by itself on one side. So wavelength equals c over nu. And we know the speed of light. That's a constant, 2.998 times 10 to the 8th meters per second. And then we need to put in the frequency, but in order for these units to cancel and give us meters, we need the frequency to be in units of 1/second, or hertz, which is the same thing. And we don't have that. What we have is a number in gigahertz. So we need to do a quick conversion of our gigahertz into Hertz so we can use it in the calculation. So 1.575 gigahertz. You can use dimensional analysis here. So we put the unit that we have on the bottom, which is gigahertz, and the unit that we want on the top, which is hertz. We think about that prefix giga, and remember that giga means 10 to the 9th. There are 10 to the 9th of the small units in one of the giga units. So now we can cancel gigahertz, and we are left with 1.575 times 10 to the 9th hertz. And so we can substitute that number in here. So the calculation, 2.998 times 10 to the 8th divided by 1.575 10 to the 9th. If you plug that into your calculator, you should end up with 0.1903 meters. So 0.1 meters, that's a little bit less than a foot long. That's a fairly large sized wave. Okay, so we've got one more wave property to cover before the end of the video, and that is interference. When waves overlap, we call it wave interference because the waves are additive. They add together their amplitude at each point to either make the wave taller or to make the wave smaller. So let's do some wave math here. Make sure I leave enough space for my picture. All right, we're going to do green waves first. So here is a wave. We're going to add these two waves together by physically overlapping them. And as you can see, according to my roughly correct drawing, the places where they hit the black line are about in the same spot. The highest point of the wave is about in the same spot. Lowest point of the wave is about in the same spot. So if you were to overlap these right on top of each other, they would look identical. And so that means that when you add them together, the wave gets taller. The highest point is now twice as high. The lowest point is now twice as low. So when you add waves together and the resulting wave is bigger, that's called constructive interference. That yields a larger amplitude for the product. Okay, and you might have guessed that sometimes the addition of waves is not constructive. Let's do red this time. So if we overlap two waves and they don't exactly line up with the position of the maximum and the minimum, then when you add them together, they cancel it. Adding a positive part of the wave together with a negative part of the wave makes the final amplitude smaller. So for this guy, since I almost perfectly overlap them, there's going to be almost no wave left when you add them together. The maximum has canceled out the minimum. This minimum has canceled out this maximum because of how they lined up. So when the final amplitude is smaller, we'll call that destructive interference. Interference pattern is an important way of recognizing that something is a wave. And this is important in the physics of how light works. All right, we have made it. Let's summarize the properties that we've discussed. So wave properties, frequency, wavelength, amplitude, speed, and interference. These are the wave properties that we care about in trying to identify whether something is a wave, and light has all of these features. And so that means that light behaves like a wave. So in the next video, we'll talk about the properties of light that don't match wave theory and that seem like they need a new theory to help to describe them.